Yeah, hi. Uh, it's a great privilege to hear in this platform. And myself, Rahul Sadish. I am a, expert senior research fellow in power system engineering in National Institute of Technology, Calicut. And yeah, I'm working as a senior engineer R&D in Bosch Global Software Technologies now, and I'm going to defend my final presentation by next week. And I got the privilege to introduce our eminent professor, Professor John Undrill here. And John Undrill has worked in power industry for more than 50 years with General Electric and Power Technologies Incorporated and Electric Power Consultants Incorporated. He is currently a research professor in Arizona State University. He's a currently is a member of IEEE and member of National Academy of Engineering. And I welcome John for this great platform and invite for a great expecting a great lecture from related to power system dynamics and the revolving areas and all. Again, welcome, John. Yeah.
Thank you. Can you see my screen?
Yes. Yes. Yes, John.
Can you see power frequency controller title page?
Yes.
Okay, well, here we go. Well,
Yeah.
good morning for me. Good evening, good afternoon for many of you. Uh, Correction first. You introduced me as a research professor at Arizona State University. I did do that for 8 years after I retired from General Electric, but now I'm retired also from ASU, and I'm still an engineer, but formally no longer a professor. Let's get going. I have to talk about I was asked to talk about power system simulation. I spent a long time doing power system simulation, and I have a long association with a couple of the programs that are used to do that. But it's more interesting to talk about power systems themselves than it is to talk about simulation. So here we go. I use simulation, but the subject is not simulation. The subject is the power system itself. Let's see if we can change slides. So about 10 years ago, there was a lot of discussion going on about how we would operate the electric grid as we got a large penetration of electronically coupled generation into the grid. There was a big concern that we would have difficulties in control and operation. And uh, at the time, the discussion was, would we be able to operate a grid with as much as 25% of electronic generation being coupled electronically? That question is no longer of much interest because there are several places in the planet now, the island of Ireland, the island of Tasmania, the North Island of New Zealand, where the penetration of electronic generation into a synchronous power system is already approaching 90% on occasions, and the lights are staying on. So the question, can we do it, is no longer the main question. The main question now is, will we be able to do it when we approach 100% uh, electronic generation? And I've pose the question again, will we be able to control the system if there's no rotating generation in it? It's in a sense a hypothetical question, because even island systems like Ireland are going to require rotating generation to remain connected to the grid for reasons other than reasons of control. But the question that's worthwhile looking at is, would we be able to control 100% electronic grid? Can we see what's going on? And if we can see what's going on, can we use that observation to control the thing? We want to operate it. To operate it, you have to understand it. To understand it and to operate it, you have to be able to control it. So we're going to talk about, can we control an all electronic grid? The answer is yes, but the answer was not yes when the subject first arose. It was should we be concerned? Uh, I still think we have reasons to be concerned, so I leave question marks at the bottom of the screen. Now, in order to understand what you might confront in operating this all electronic system, it's useful to understand how we operate the system and how we control the system now. We control the system now in the same way that we have since perhaps the early 1950s, and we'll talk about that. We're talking about controlling a very large machine with many rotating turbine generators in it, spread over a very long distance. In the system that I have worked most often with, the Western system of the USA, the system spans an area of 1,000 miles north to south and 800 miles east to west. The idea that you can have instantaneous communication from one part of the system to the other is a very expensive hope. And you have to remember that every time you draw a block diagram on a sheet of paper, you've got to be careful that you're not connecting something in British Columbia and Canada with something in Mexico and hoping that it'll work. You can get information from British Columbia to Mexico, of course, but the latency of the signal is as important as the sampling rate. And we have to remember that. We're dealing with a system, when we talk about the rotating synchronous power system that we deal with now, you're talking about a system whose behavior is dominated by time constants of the order of 5 seconds. The inertia constant of a turbine generator is somewhere between 2 and 5 or 8 seconds. And the field winding time constant of a synchronous generator, rotating generator, is somewhere between 4 and 12 seconds, perhaps. So you're not going to be able to make things move instantly. You're not dealing with a rabbit, you're dealing with an elephant. We'll talk about this aspect of a power system. We'll treat the electric transmission network as a large, 1,000-mile long, 1,000-mile wide interconnection, making sure that the rotors of generators turn at the same speed, making sure that the induction motors turn at a speed determined by the frequency of the voltage wave on this AC system. But we're not going to study this AC system. My interest is, how do we control the power system? By controlling the things that we can put our hand on. The things we can put our hand on are the reactive power controls of generators, which are related to voltage, and the real power controls of turbines, which are related to speed and frequency. So we're talking about this when we talk about today. We're talking about this when we talk about the perhaps a 10-year future. There's plenty of this today. There's a lot of this now. This is in the USA, 30% coal, 30% gas, and the balance is nuclear and renewable. The way you control the power system, when we talk about controlling power system, we're talking about the ability to control the power flow on lines, the frequency of the voltage wave, and we control those by controlling the speed and the power of rotating generators. The control of a generator is delegated to the governor. The governor does not control speed, and it does not control power. It controls the relationship between speed and power. Its job is to make sure that the speed of the turbine, which is, of course, the same as the speed of the generator, is related to the power that's developed by this drooping line. If every owner of every generating unit on the system agrees to operate according to this rule, you have very effective control of the system. If I have 2 generators on, for example, and at some moment the first generator is operating at a power level A, and the second generator is operating at a power level P, and everything's sitting steady and running very smoothly, and then I experience a sudden increase in load. Perhaps somebody turns on a large compressor in a liquefied natural gas facility somewhere, and I have a large increase in load. then the speed is going to have to go down. The speed will go down from N1 to N2. The power of generator A will go from N1A to N1D. The power of the other generator will go from N1P to N1S, and I'll wind up running at a lower speed. But with the power developed, the change in power allocated equitably between generator A and generator P. If I want to bring the speed back to 50 hertz or 60 hertz, then I need to raise the speed reference setting here to here or here to here. If I raise the speed reference settings with the power remaining constant, then I'll change the frequency. If I wanted to redistribute power between two machines so that I start out with the machines running at here and here, and I want to equalize the speeds, then I would have to raise the setting, the speed reference setting of this generator from here to here, and lower the one from the other generator from there to there. I'll have effective control of the speed if the power remains constant, or of the power if the speed remains constant. This is referred to in the industry as the primary control system of the power system. The primary control of a rotating mass is implemented by the governor. The governor is controlling the relationship between speed and power according to the sloping, drooping line. Now, in order to understand what's going on, we need to reduce the qualitative description to some math, and a little bit of algebra does this. Here's the drooping control line that we want to impose on, want to honor in the rotating generators. That line represents that equation. We've assumed for most of the life of the industry, since perhaps 1900 through perhaps 2000, that the load on the power system would not be constant, but would increase as the speed increases. Well, if you think of the load being light bulbs, this is not true. The power would be constant as speed changes. But if you think of the load as conveyor belts and quarries and factories and around the power system, as the speed increases, the load increases. And it could be linear if the load is conveyor belts and things like that. It could be a power law, a square law, or a cube law if the load is pumps or fans. Well, a lot of the load is pumps and fans, and we normally characterize the load on the power system by taking a linear approximation of the change in load with change in speed, and we use the index D. So we can say power increases as the dth power of speed. Well, if I characterize the load on the system by that, and the production of power on the system by that, and I can require that the generation equals the load, and I do some algebra, this and this combine to give me this. If I have a change in speed, if I have a change in generation, I have a change in speed if I have a change in load, and the speed change will be related to the change in power by the regulation or the droop factor R of the drooping governor relationship and the D factor that I use to characterize the load. This has been in use for 80 years. In the last 20 years or so, we've recognized that not every generator connected to the system contributes to control. There are a lot of generators that prefer to run at maximum power and not be maneuvering as the load maneuvers. Well, by balance, the load must balance, the generation must balance the load. But every generator doesn't need to contribute to balancing generation with the load. And typically, about 30% of the generators in a typical power system will maneuver and contribute to the solution of this equation. And the other 70% will operate at fixed power. The generators prefer to operate at fixed power in many cases because of the fact that their machinery is thermal. Temperature range in a gas turbine is 1500 degrees centigrade. And change in temperature causes expansion and contraction and internal stresses in the machinery. And the operators don't want to do that. So there are good reasons why many power plants don't operate under drooping control. And this K-rig is not one. We'd like it to be one, but it's frequently 0.3. Now let's go on. So let's consider this. I have a little power system running somewhere. It's not connected. It's connected within itself, but it's not connected out to a very large grid. It could be a couple of gas turbines on a gas production platform in the North Sea. It could be a large paper mill somewhere in Scandinavia operating with a hydro generator and a steam generator. It could be a refinery somewhere in India that, because of an emergency in the transmission system, is operating with its own generation, separated from the local grid. Let's assume that we've got two equally sized turbines, let's say 200 megawatt turbines. They're both operating with an equal droop, so that slope of that drooping line is 5%. One of them's a hydro unit and one of them's a steam unit. Same size, same droop, same load. So here they are operating each at 75 megawatts. And somebody turns on a large block of load. Somebody starts a large chipper motor in a paper mill. Somebody starts a large compressor in a LNG facility. A rolling mill starts up in a steel mill. But there's a sudden increase in load. The load goes from 75 megawatts to 80 megawatts. Load goes from 150 to 160 megawatts, but each generator is required, would be expected to produce a half of that change. Well, here's what, this is a simulation, but it's pretty good simulation. Here's what happened. The load increased at the 10-second mark, and the generators did not go equally to their new load. One generator did most of the work, and the other generator was lazy. The red is characteristic of a steam turbine response to a sudden change. The blue is characteristic of a hydro turbine response to a sudden change. Our droop equation, this equation, or this equation, depending on who's regulating. Let's assume it should have been this one. Our droop equation didn't work. The droop equation said that the two units would go to an equal output, and they didn't. Why? Well, this droop equation only tells the end of the story. It tells where we expect the power to go, where we expect the speed of the machine to go, but it doesn't tell us how it goes. It only tells us where it's aiming to go. We need more. We need to see the beginning of the story, and that's determined by, of course, by the Newton's law of motion. And so this is the Newtonian dynamics in rotation. This is the polar moment of inertia of a rotating turbine generator. This is the power developed by the turbine, and this is the power consumed by the load. When the power and turbine power and load power are equal, the rate of change of speed is zero. If there's a sudden change in load and no change in turbine power, then the speed will change. Well, if we recognize both the droop equation and the Newtonian dynamics equation, then we could see this. We could see that when the load increased, the speed started to decrease. Frequency decreased on the network, rotational speed on the rotating machines decreased. They did not, the two machines, red and blue, did not go down equally because the electric network is elastic. It's not a rigid connection, so the speed of all generators on the synchronous network is not 3,000 RPM in India for a 50-cycle machine or 3,600 RPM in California for a turbine machine. The speeds are a little bit different from each other as the whole connection of generators jiggles around a little bit. I call this the sizzle of speed. The speed of the machine goes from here down to here and then follows to here with a sizzle superimposed on it. Here's this is the same graph as we saw before. Well, that's not the whole picture. Here's the whole picture. I ran the simulation not for 30 seconds. I didn't look at what was going on for 30 seconds. I looked at what was going on for 5 minutes. This nadir here is this nadir here. This peak of steam turbine power here is this peak of steam turbine power here. So if you watch for 30 seconds, you get a false picture of what's going on. You get the impression that one machine's doing all the work and the other machine's taking it easy. In fact, if you wait out the natural characteristic of the system, this equation tells you where you're going here, and this equation tells you how fast you're going to dip in frequency here. Well, that's how the power system works. That's universal. It's not widely seen. The various people that are doing it don't necessarily think in terms of differential equations and graphs of made in MATLAB, but this is how the power system works. Now, consider this. That's graphs and theory. Let's think about what would happen and what it feels like in reality. So here we are sitting in the control system of our power system, in control room of our power system. The oil refinery is running steadily. The paper mill's running steadily. The town and somewhere in northern Canada is running steadily with the lights on and people watching television and the electric heaters working. And something happens. Mother Nature delivers a lightning stroke to a transmission line, and that disconnects both the transmission line and some generation. Or a large motor starts up, a cooling water pump in a refinery somewhere starts up and switches on a large load. So there's a sudden unbalance between generation and load. Here's what happens. The frequency is going to go down in accordance with the Newtonian dynamics, but it does so in a few seconds. I'll go back one slide. This is from the moment that an event occurs until the event is all over is 20 seconds. From the moment that the event occurs until the frequency reaches a minimum is, in this case, perhaps 3 seconds. In 3 seconds, the guy in the control room can't do anything. He's not even looking at his screen, perhaps, at the time that the event occurs. And by the time he turns around in his chair and reaches out with his mouse to see what's going on, the event's all over. So the system did something, responded to the event without any action from the control room. Speed changed according to Newtonian rule. The speed and the frequency settled as required by the droop equation. Here's such an event, not in simulation, but in reality. This is the frequency of the Western USA grid over a minute from 0 to 60 seconds when a large generator tripped off the line. This was a very large generator. This is an event that occurred when basically an 800 megawatt generator tripped off the grid when the load on the grid was about 100,000 megawatts. Frequency went down by 1/10 of a hertz and recovered decisively and settled out according to the droop equation. That's a test recording. The parameters that were used are in. I just want to show you are time constants in the order of seconds. Inertia time constants of the order of 2 to 5 seconds, and the governing fraction. 30% of the plants in the system were contributing to control. So we modeled the power plants and rotating inertia by Newtonian dynamics. We've got to recognize that if I increase the load, I have to increase the turbine power. The load assumes the privilege of turning on the light switch and having power delivered. It's not the load sends an email to the generator and says, please make some more power. The load turns on and the generator is expected to respond. So we need to describe the power plant, which is the surrounding equipment around this rotating mass by a transfer function. Here's what we want. We want the plant to respond so that the change in speed is related to the change in power by a droop. This is what we want. Here's the transfer function that says what you get, which is this, is related to what you want by this. It's an implicit relationship, and there's some algebra to be done. We're not talking about algebra here. Here's the differential equation of the transfer function diagram. This is G of S. This transfer function, G of S, transfer function of the power plant, for a steam turbine could be as simple as this. Here's the droop, R. This is a gain of 20 if the droop is 5%. Time constant of valve motion. This is a mechanical linkage that's moving a steam valve in response to the motion of a governor. The governor is today is electronic, but 20 years ago it was still a mechanical flyball governor. And this is the dynamics of perhaps the steam turbine and the boiler. Here's a more complicated one. This is what we use to represent a large single shaft gas turbine, perhaps a 250 megawatt frame 9 gas turbine somewhere in the 50 cycle world, a little bit smaller machines for 60 cycle world. The governor is a proportional and integral controller. There are temperature limits which are implemented by a proportional and integral gain, and a whole lot of interaction between various signals. The loads are also no longer to be treated as constants. For many years, we used this to represent load, mainly because, for two reasons actually, because the computers available to us in the 1960s, when this was all originated, were not big enough to store anything more elaborate, and because we didn't know enough about what the loads did, because we didn't have the SCADA systems and the PMU phase of measurement units that we take for granted today. We represent the load today on the basis that in the large electric grid, the load appears, let's say, at 66 kV as a 30 megawatt load on a substation. But in reality, the load is from below the substation is a substation transformer, an 11 kV bus, an 11 kV transmission line, and in motors of various sizes and types, electronic load like battery chargers or resistive heating, and static load like the outdoor air conditioners that are almost universal in hot climates, where your air conditioner has an outdoor compressor driven by a motor and an indoor air handler. So there's what we saw in an event, big event in the Western grid. Here's simulations of that event, and I want you to observe that the simulation clearly matches in principle what happened in reality. Reality, simulation, reality, simulation. The simulation sensitive to what we assume about the inertia constant of the rotating machines. If all of the machines on the grid were aeroderivative gas turbines or hydro units, you might be following the green curve here, and the frequency might have dipped down to whatever it went to. I'm not going to read the number. If you increase the inertia, you do two things. You decrease the initial rate of fall off of frequency because it's a larger mass and as Newton's law of motion applies, and you slightly decrease the amount by which the frequency dips. You have an effect on the rate at which power is delivered. If you know the inertia of the system, you should be able to get your simulation to match reality, so that this is reality and this is a simulation, and you can believe what you see in the simulation. You do this simulation with programs like PSSE or PSLF, Power World. There's a DigSilence, a European program that does this. There are half a dozen trusted, well-proven simulation programs, which if you set out to simulate what the grid does in reality, will get a very good approximation to what it does by mathematics. Here's the behavior of the Eastern USA grid in a bad event where a lot of generation was lost very suddenly. and the frequency dipped a little bit further than perhaps the simulation would have anticipated, and then didn't come back. Now, in 6 seconds from here to here, people in control rooms can't do anything. They see the screen change, they see the warning message on their screen, but you can't do anything in 6 seconds, and you need to think before you do anything anyway. But by a minute later, the fact that this frequency has gone down and has not started to recover would be starting to get people worried, because the behavior of the system must, to be successful, recover back to the 60 cycles. This is not where protection is going to operate and trip generators. It's not where under frequency load shedding is going to operate, but it's indication that things are not coming back the way they should. Here's a recording from basically all of North America recording system run by one of the universities in the east of the USA. There are many machines here sizzling, but all rotating at a common speed. This is a sizzle that I talked about before. This is a simulation of the Western grid when a large block of generation was lost. And you see frequency changed very rapidly when a small event occurred first. And then when a larger block of generation tripped about 2 seconds later, frequency went down. And again, it sizzled, but you can look at the mass of the system and say it goes like that. So today, as we control the power system, we can trust the governors to do what they need. The primary control of the system, which is the governors operating on the fuel valves of the turbines or the water valves of the hydro plants, does the right thing. It doesn't have to be instructed what to do. It inherently knows what to do. It opens the gates when the speed goes down. It opens the valve as the speed goes down. They do it very quickly, and they do it autonomously. You don't need an elaborate communication and command structure to tell the governors what to do. They're going to respond to a sudden event correctly and effectively. And I won't go back to the slide, but the time constants characterizing the governors are of the range of 50 milliseconds to perhaps 100 milliseconds. So the present power system has a strange characteristic. The thing that's being controlled has long time constants, 5 and 7 seconds. The controls that are operating on it are mechanical and thermodynamic and hydraulic, and they're characterized by time constants of tens of milliseconds. It's rather impressive to stand in the turbine pit of a hydro turbine when one of these events happens, perhaps in a test, and see this very large machinery, hydraulic jacks with 50 centimeters diameter and a travel of a meter, moving with a time constant of perhaps 300 milliseconds. Things vary slowly. The generators operating in droop mode do what's required. They do it autonomously. They do it naturally. They're not dependent on high bandwidth communications. When things are moving slowly, the droop equation is a pretty good description. So there's a summary of the legacy of the system we're aging out. We're getting rid of coal burning plants as fast as we can. There's a conference going on in Egypt now discussing that subject. It's not going to be easy if your natural resources make you dependent on coal, but eventually we can expect that the large thermal plants will disappear. We are going to an all electronic generation and load system. The generation will be electronic, solar panels with inverters. The other part of the electronic generation will be wind turbine generators, reducing power at variable frequency, maintaining the charge on a DC bus capacitor, and being turned into AC 50 or 60 cycle power by electronic inverters. The system will always have some rotating inertia. The concern of recent years that we're going to have no inertia in the system is not going to happen, because there are still going to be many places where synchronous generators fired by fired steam boilers are going to continue to operate. Paper mills are still going to burn their black liquor and use the heat to make the electricity they need to run their paper mills. Refineries are still going to need heat, and so they're going to have to burn their waste petroleum products, and they're going to turn the heat into electricity to drive the pumps and machinery that runs their refinery. Steel mills are still going to have rolling mills. Large LNG processors are still going to be running electric motors to run their drives. And so the electric system will, on the load side, even if not on the generation side, still have some rotating inertia. It'll be much smaller than we're used to, but it'll still be there. Well, here's the now, so we're switching gears. We're going from rotating a power system with steam and gas turbines and rotating loads and transfer function diagrams like I showed 5 minutes ago. Here's the transfer function diagram for an electronic controller where the energy comes from solar panels or a battery at DC, and the inverters are controlled to run the AC power system. This controller operates in the droop relationship. You don't see the droop. You see the reciprocal of the droop. But this sheet of transfer function information is how the inverter would be controlled in an electronic solar generating facility to cause that facility to operate according to the droop law, where the speed goes down with a slope of 5%. Well, that diagram is presumably authoritative. I understand it if I really need to, but most of the time looking at it gives me a sore head. I tend to simplify that diagram and rearrange it like this, so that I have an inverter, which is an electronic device. It can be controlled to control voltage, so it measures voltage and compares voltage with a set point. It can be operated with a droop, and the reciprocal of this gain gives me the droop of the drooping relationship, which goes down from speed load reference up here across the page to a reduced frequency at high output. So this controller, blue and pink, controls voltage according to a drooping relationship between voltage and reactive power. And this controller compares frequency with frequency set point and controls real power according to a drooping relationship between a set point for either speed or power and actual power output over here. I'm shadowing the drooping relationship as I speak. The voltage controlling part of the system wants to control that component of current that relates to that accounts for reactive power, and the real power, the frequency controller, wants to control that component of current that relates to real power. The controllers operate on the amplitude and voltage of a voltage controlled source. So if we go back here, the generator can be represented as a Thevenin equivalent with a voltage controlled source where we have control of the amplitude of the voltage, we have control of the angle, and there's an impedance of the Thevenin impedance for the system, connecting it to that large transmission network that we were that's operating at a common frequency. Well, let's just look at what we can expect in the next if we had a 100% electronic system. So let's just look at what happens if you have a sudden load increase or a sudden unbalance of load and generation, to call it a sudden load increase, in an all predominantly conventional system, rotating hydro machines, rotating turbine generators. And let's assume that the system's 3/4 rotating and 1/4 electronic. So there's 3,000 megawatts of steam turbine and gas turbine generators, hydro generators, and there's 1,000 megawatts of wind and solar. Suddenly increase the load by 2%. So 3,000 megawatt, 4,000 megawatt system, 80 megawatt load increase, which is 2%. That's a very large disturbance in relation to the normal operation of, let's say, the Eastern or Western USA grid or Western European grid. It would be a large event in relation to the two large grids that exist in the Russian world. And it would be a very large event in relation to any of the state electricity board systems in India or the electric system of China. So this is 2%, which is two large nuclear units disappearing in a 100,000 megawatt system. Frequency goes down. This is mislabeled. This is frequency. Starts at 60 hertz. 2% loss in generation. Frequency dips to 59.88 and recovers, and we've seen that shape before. If everybody would contribute to control, you'd see the red response. If only a half of the rotating generation contributes to control, because a half of them want to stay at constant output for metallurgical reasons or revenue reasons, you'd get a bigger dip in frequency and you'd settle a little bit lower. If the rotating generation did not contribute to regulation and left all the regulation to be done by the electronic generation, then the electronic generation would have to do all the response. So frequency would settle down here, and the response of the power of the electronic generation would go up here, and you'd still be able to do it. We've never seen that yet in any of the electric grids that I'm familiar with. Perhaps on shipboard systems, which are a little bit specialized, it may have happened already, but you wouldn't want it to happen. You'd want to bring the frequency back up to where it should be, which would be perhaps somewhere between here and here. Now, once the frequency is stabilized, and this is a minute, this is 50 seconds across. So once the frequency is stabilized, of course, then you can bring it slowly back to 60 hertz or 50 hertz by using secondary control. Secondary control, when I was basically a graduate apprentice, early days, was a young engineer walking along the turbine floor, or the governor floor, grabbing hold of the hand wheel of the red generator and moving its set point up a little bit, walking along 50 feet to the hand wheel of the next generator and moving its speed load reference up a little bit. Nowadays, of course, this is not done by young engineers walking around turning hand wheels. It's done by digital computers operating automatic generation control, which is considered to be secondary control, supervising the operation of the primary controls, which are governors. Frequency load event occurs, frequency dips, governors respond, stabilize the frequency at a slightly reduced value, and then secondary control brings it back up. So system sits stably, event occurs, power starts to increase according to primary control, comes back to a elevated but not sufficient value, and then secondary controls bring it up to the amount that it finally needs to be. And the time scale is 50 seconds or a minute. Now let's reverse the discussion. Instead of a system that's predominantly rotating, hydro and thermal, let's look at a system where the system's predominantly electronic, with a little bit of sort of leftover rotating capacity. So let's look at this 4,000 megawatt system, 3,000 megawatts electronic, 1,000 megawatts of rotating generation. Its inertia constant would be 1, but we're not going to worry about that too much. But for those that really want to know remember about inertia constant, it would be 1. If you cut the rotating generation in half, it would be 7/8 electronic. Or let's go to the extreme and say, just could we control this thing if it was 100% electronic? Let's consider the same event. So 4,000 megawatt system, 80 megawatts sudden unbalance of load and generation, and look at what happens. Well, here's what happens. And it doesn't look radically different from what happened in the other case, except where we were looking at a span of 50 seconds with the conventional system, We're now looking at a span of 5 seconds. Where the event occurred from here to perhaps here, with the nadir frequency occurring at 5 seconds with the all rotating system. Now the event occurs and the thing is settled out within a quarter second. This is 5 seconds across. If I take this and expand the time scale, it's settled out. The oscillations have gone away, and it's more or less in steady conditions in about a quarter second. So things are happening very much faster than we saw with mechanical control of rotating masses. Let's go to the next slide. So this is the same. This is the same 5 second plot of frequency from the previous slide. Here's what the power of the electronic generation would have to do in order to stabilize the system like this. So this is a 5 second span. Frequency settled out more or less within a quarter second and settles to a steady value. Not at the original value, but according to droop, according to the droop equation. And then ready for secondary control to bring it back up. And secondary control would bring it back up over the next 2 minutes, perhaps 3 minutes. Here's what the electronic power needed to do in order to stabilize the system. If the electronic power was 1,000 megawatts, it would this is the power of the electronic generation doing what it needs to do with a little bit of help coming from the rotating generation. If there's a little bit of rotating, a lot of rotating generation, 1,000 megawatts, the electronic power needs to follow the red line. As you decrease the amount of rotating generation, and decrease the inertia of the system, you both change the nadir of the frequency dip, which we saw on the previous slide. As you decrease the amount of rotating generation, you increase the depth of the frequency dip, and you require the electronic generation to maneuver a bit less. When it's all electronic, of course, the electronic generation has to do all the work, and it does it in a fraction of a second. The model, this was done by, this is of course not reality. We haven't ever seen this happen in reality. We're anticipating or speculating that we may see all electronic systems in the future. The voltage issues are handled by manipulating the amplitude of the source voltages in the electronic inverters. The frequency issues and power issues are controlled by manipulating the phase position of the internal voltage, the Thevenin voltages of the electronic inverters. Well, what I wanted to convey with this exercise of going from all rotating here to all electronic here is the droop principle of control works very nicely. It works much more quickly than before, but it works very nicely when everything's electronic and everything's happening very quickly. Last slide that I made late last night when I wanted to have a look at this. This was done with the system being all electronic. There's no rotating equipment connected directly to the electric grid. The electric grid is 3-phase transmission lines on towers and cables in ditches, as we've had for the last 120 years. The generation is all electronic. It's type 4 windmill generators with electronic inverters, batteries with electronic inverters, solar panels with electronic inverters. The load is entirely electronic. So it's either LED lights or it's inverter-driven air conditioners on the sides of apartment buildings in Singapore, or it's the electronic drives of a large steel mill somewhere in Brazil. But everything's electronic. There is no direct connect of synchronous machine devices to the electric network. And yet the behavior is still has the same basic characteristic of a dip to a frequency nadir, a recovery about a halfway back, and then secondary control to take care of the realignment of everything over the ensuing minutes. I changed my simulation model late last night and said, let's assume that even though the generation's all electronic and the load is all electronic, that's not true. There's 20% of the load is still synchronous machines or induction machines connected to the grid directly by contactors, but no electronics between the grid and the load. Well, that's probably a safe assumption because the induction motor fleet of the world is not going to go in 100% electronic in the next 10 years. It's going to, the induction motor fleet of the world is going to become more electronically connected as electronic prices and so on go down and as equipment's retired. But we're always going to have rotating equipment, principally induction motors, directly connected to the grid. If I do that, then there's a big change in what I see. Instead of seeing the frequency dip in a quarter second and recover about a halfway with a little bit of oscillation, which I may or may not be worried about, frequency dips much less. It's a small, as I set up 20% of the load being conventional induction motors, the frequency dip, which would have gone down here and come back to here, is much more gentle. If the inertia constant of the induction motors, that is the polar moment of inertia of the motors, is small, I'd see the red response. There's an effect. The effect is decreased as the inertia constant of the induction motors is increased. This would be an induction motor driving a cooling water pump somewhere. The diameter of the pump and the characteristic of the pump is smaller physically than the diameter of the motor. This would be induction motors driving high-speed compressors, where the inertia of the driven load, the compressor that the motor's driving, is greater than that of the motor itself. If you look at frequency dip is affected by the thing that the motor is driving. The motor speed itself, of course, is less than the synchronous frequency because we're talking about induction motors. But again, as you have a low motor inertia, you have a slightly faster rate of decrease of frequency. Enough of that. So where does I took the power developed by the electronic converters when corresponding to this event, and you see that as the motor inertia is increased, the amount of power that is consumed transiently is quite significantly affected, but the settling point, according to the droop equation, is always the same. So what do we see? What can we foresee for the control of the grid, perhaps 10 years from now, when we will start to see the thing become very nearly entirely electronic or entirely electronic? Well, I argue this is not the only possible trajectory that we could face, but it's a possibility that stands up to examination using simulations with the tools that we have available to us now. PSSE is widely used around the world. PSLF is widely used in North America. DigSilent and various other programs are used in other parts of the world. And according to the simulations that we can do of the anticipated future condition of the system, we will be able to continue to control it according to the droop relationship. That has a great advantage that it's not dependent on broad bandwidth control between places. Remember, this droop control system that we use is not all in one place where you can communicate between one machine and another in milliseconds. It's spread out over thousands of miles. So it's very important and very significant that we're going to be able to control this large all electronic grid, not depending on broadband with low latency communications. And the simulations show that it's going to work quite nicely. It's going to work much quicker than we've seen in the past, but it's going to work. Primary controls will have to be tuned to be quick responding. And the response of the equipment that we see will be correspondingly fast, but not necessarily as fast as you might believe, considering that an inverter can probably maneuver the amplitude of a voltage in a half a cycle. You're not going to see equipments responding in a half a cycle. You're going to see equipments responding in tens or hundreds of milliseconds. The primary control will still be local and autonomous. You will not be dependent. We don't have to be dependent or become dependent on broadband bandwidth control. We had a bad problem in a steel mill that I was involved with 20 years ago, where we had a control system that depended on signals being sent from turbine generators on the east side of the facility, about 4 kilometers away, to a large rolling mill on the west side of the facility. It was only 4 kilometers, but the relay equipment we used, which was the best that we could buy from the current name brand manufacturers, claimed that contact outputs would go from one relay to the other instantaneously. When we tried it and got our oscilloscopes out and looked at what was really happening, there was a time delay in signals going from one part of this control system to another of 50 milliseconds at the sending end and 50 milliseconds at the receiving end. We were sampling the signals that we needed to measure at a rate of 60 times per second. We were perfectly okay with respect to Shannon's theorem and sampling theory, but the 100 milliseconds of transport delay that is latency, that we were getting between the signals being sent and signals being received was enough to destabilize a controller that we had on one of our engines and generate an unstable oscillation. And so I'm very, very much concerned that we can get the control of this system without depending on broadband with low latency communication. We want the control systems in these widely spread places, 1,000 miles apart, to be able to act autonomously and act correctly when they act autonomously. I'm optimistic. I believe the present control protocols that we've been using and that we understand are going to be up to the task. The secondary control will, of course, be needed, and the secondary control will certainly be advancing over the next 10 years as our electric system evolves, as is everything else advancing. But it does not need to become preoccupied with getting ourselves down to very low latency and having a broadband with control. Secondary control can continue to operate on a much more economical use of bandwidth and the communication equipment. The simulations that I showed you and were made with the tools available for production use today. They were made with tools that represent the AC electric system by phasor mathematics, where the phasors rotate at either 377 radians a second or 314 radians a second. That's not going to be sufficient to tell us what goes on inside the electronic inverter equipment that's in the loads and the power plants. We need to have an evolution of our simulation technique so that we can see what's going on on the basis of a point-on wave where the sinusoidal voltages in the system are represented by the differential equations of inductance and capacitance, and the network is going to have to be modeled in an electromagnetic transient level. That's going to require that instead of running simulations with time steps of 4 or 5 milliseconds, which is what we can do with the present grid simulation tools, we're going to have to run simulations with time steps of 4 or 5 microseconds. That's going to make it impossible to run a 100,000 bus grid simulation in 10 minutes, which is what we can do now with a fancy laptop that we can buy in a consumer electronics store. We're probably a couple of generations of computer equipment away from being able to run our simulations with our point-on-wave modeling of the electric system and with the insights that we'll gain for that. I'm a little bit envious because I'm not going to be doing that. I had my fun with the phasor positive sequence representation of the electric transmission network with symmetrical components and phasors running at 50 or 60 cycles. Many of you are going to be in the power industry running simulations and understanding the grid much more on the basis of the point-on-wave characterization of the AC electric system, and I hope you have as much fun doing that as I had dealing with the 50 phasor representation. Thank you for listening, but let me just throw this up as a parting thought. I went looking as I was preparing for this talk, and just went looking to see when were the first papers in IEEE or other publications describing what we're talking about. What were the date of them? And I was expecting to find papers dated 1915 or 1920 or perhaps 1930. The first paper I found on the governing of rotating machinery was written by a guy in England and published in 1868. The guy that published it was James Clerk Maxwell, the father of the electromagnetic spectrum. And he was dealing with steam engines and the properties of heated gases and thermodynamics. So there's nothing new under the sun. Thank you for listening.
Yeah, it's a very informative session, sir. Am I audible, sir?
Just a minute, my headset.
Yep. Am I audible now, Profs? Yep. Yeah, Professor, you are on mute. I think so. Yeah, I'm audible. Yeah, now it's
Yeah, now
yeah,
you can hear me. Okay.
yeah. Yes. So it's quite informative one and a very basic. I think it's much comprehensive for the primary and secondary control of load frequency control, and that depends on how it depends on the inertia constants and all. And for the first, we can go for that comments from the audience. Yeah, nothing is there. I think so. Um, if audience, if you want to have any questions related to this a particular area, you just chat in the box, and I will convey. So one question is that we are dealing with so many inertia, because this topic is a huge research topic, and a very informative one is the last you presented on governors of Maxwell. I was really striking when I joined my research. A senior professor in my college, actually, Dr. Abraham D. Matthew, he suggested that yeah, go to the library and see the IEEE transactional power apparatus from 1975, and and go with that for the basic studies of power system stability and all. don't depends upon only the Prabha Guntur textbook and all. So I just remind that you said at the last session. Yeah, yeah. One thing I want to ask that there is so many researchers are going with the inertia concept. So, what do you see the major challenges in the research perspective? Um, what industry faces actually? Different load components will be there. There is so many numerous loading will be there. Not at all depends upon the motor side and all. So, what you are predicting? What you are suggesting that major research challenges in that particular area due to inertia aspects?
Okay. I'm happy to respond to that. Can you hear me?
Yeah.
Okay. So I'm not using a headset now. If there's an echo, please tell me. Well, look, what I was talking about was basically the control of the ability to maintain control. But I don't think that's the problem that we have right now with respect to electronic generation. I think that there's the big difference that I see between electronic generation, which is coming, and rotating generation, which is going, is this. When there's a sudden electrical event on the transmission grid today, where you've got let's say insulator flashes over on a 500 kV transmission line, or a rat gets caught up in the 11 kV buswork of a plant auxiliary system, or something happens electrically that causes an electrical short circuit and thereby causes circuit breakers to operate. We know what the machinery in the system is going to do. We know how synchronous machines behave when there's a sudden change in the characteristic system that they're connected to. We can put the machines on the test bed in the factory and put a short circuit on them. And we know from 100 years of experience that a synchronous generator, when connected to the grid in a sudden grid disturbance, is going to do a predictable thing. There's going to be a high short circuit current. It's going to have a DC offset component in the fault current, and it's going to follow the electromagnetic laws very closely. Look at a synchronous machine built by Siemens in 1910, or a large synchronous machine built by General Electric in 2005. Characteristics of their response to an event are very similar in principle. They have the same shape, characterized by transient reactance, subtransient reactance, synchronous reactance, time constants. They're well understood. The
Yes.
trouble, the thing that we face now with electronic generation is that we don't know how it's going to behave when there's a sudden disturbance outside the equipment in the electric grid. It's going to behave according to controls that we can't see. When we run PSSE or SLF or Power, looking at simulating the electric grid and the generators connected to it, we're simulating what goes on in rotating synchronous machines and what goes on according to phasor arithmetic in an AC system. But we're not simulating what goes on in the IGBT, the H-bridge circuits of the inverters. That's by the control system of the inverters. And we don't know from experience how they're going to behave. I get into conversations with people operating who are facing uncertainty as to what's going to happen with the electronic generation. Ireland a little bit, South Australia, where the sun shines enough to do a lot of electronic generation, a little bit in the northwest of the USA, and various places with a lot of particularly solar generation.
Yes.
The thing that's of concern is we don't know. We don't know by mathematics and simulation. We don't know by test and proving experiments. We don't know by operational experience yet how these electronic converters are going to behave when things go wrong on the electric grid. Now, when
Yeah.
you're talking about a textbook example of a single phase fault cleared in 4.5 cycles on 115 kV transmission line,
Mm.
we get a lot of those, and we're starting to build up some experience. But when you're
Yes.
talking about an airplane flying into a 345 kV transmission line, or a bad earthquake taking out a very large power plant somewhere, or a forest fire, or a brush fire causing transmission lines to trip because of smoke, where the things that you study in short circuit considerations are not able to be understood by the simulation programs that we're using. We're
Hmm.
very much in the dark, and what it's generating is the situations where electronic solar panel plants or wind plants put into service on the basis of the best intentions of the manufacturers, who've done the best they can to simulate these equipments with electromagnetic transient programs and electromagnetic transient simulators, and even test operations, according to their best intentions and best efforts, best knowledge. These quite large generation facilities are going to respond according and in a way that can be understood by the phaser uh, representation simulations, just as we go. In fact,
Yeah.
we don't have enough experience to be confident in that, and so we're
Mhm.
having to build in and make sure that we have safety margins, capacity margins that,
Yeah.
that
Yeah.
have to be larger with this
Mhm.
equipment, whose whose I can't say reliability, but I have to make
Yeah.
a statement. We can understand, we can have faith in synchronous generators because we've watched many years.
Yes.
We
Yes.
understand.
Yes. Yes.
We can't have the same faith in the electronic generation because we don't have the experience, and
Hmm.
our analytical tools need to be advanced quite a lot before we'll even be able
Yeah.
to have our understanding from that analysis.
Yeah. I don't know the relevance. I think so. In our lab itself, we are developing a virtual synchronous generator through HIL systems and all. So I don't know the industry perspective, what they are doing with that when comes to inverter based resources. So yeah, that area too, I think we can discuss in the virtual synchronous generator regarding VSG and all
Okay.
related to inertia. Yeah. The professor, one more question in the chat box. I will read for you. After a grid disturbance, what would be the frequency response of the grid without any frequency response measure working?
Yeah.
That's the question.
Uh, I don't think the simulation models that I was using for the talk today won't give me an answer to that. The answer is it has to come from a combination of what we can learn with electromagnetic transient level simulation, where we can see whether the control system that's gating the IGBT transistors and the inverters will be able to continue to make the inverters work, and we'll have to be able to understand what the uh, load that's connected to the grid will do. We don't know we, we don't know yet what's going to happen if the grid's all electronic. I think I can anticipate what will happen if you have the intermediate situation. Visualize that we have an electric system that, instead of being uh, 80% rotating and 20% is 80% rotating and 20% electronic. If all the electronic generation disappeared instantaneously, We know what would happen. We can trust our simulation programs to tell us what will happen if you have a sudden 20% deficiency of generation. You'll have load shedding very quickly. The load shedding relays, there would be some questions about whether the load shedding relays that we use, electromechanical relays and the GE and Siemens and ABB under frequency relays that we use today, would operate quickly enough. You lose 2% of generation, frequency goes down quickly, load
Yeah.
generation, load shedding works, and load shedding is quick enough that you recover. If you lost 20% of your generation, we sort of know the answer, because the oil and gas industry, where you have production platforms in the ocean and large isolated LNG plants, would typically have four, 5, or 6 large generators serving the entire load of their facility. They know that if
Mm-hmm.
they lose one of 3 generators, that you don't need a computer to know what's going to happen. Everything's going to
Mm-hmm.
stop. If you lose 1 and 4 generators, it's of white knuckles. You may or may not, you're going to have a lot of load shedding and very white knuckles. If you lose 1 and 5, you might be okay.
Yeah.
If you visualize the electric system of the Western United States losing 20% of its capacity, that would be suddenly losing all the generation in Washington State.
Mm-hmm.
Yeah, you don't need a computer to know what's going to happen. The lights are going to go out.
Yeah.
If you're talking about an all electronic system and you're an optimist, you perhaps could argue, well, they could change their mode and they could. Uh, no, they can't, can they? They'll have even less overload capability than we have in our present system. Our present synchronous generators would not be damaged if they were subjected to 3 or 4 seconds of too brief flow.
Yes.
They have a lot of thermal inertia. If you're talking about inverters implemented with IGBTs, and you had a sudden disappearance of generation, uh, you lost 20% of your generation, then the remaining generation will have to increase its output by 20%, 25% actually. It won't. If it's already at maximum, going to it's going to disappear very quickly. It's going to see its overcurrent,
Yeah.
regardless of its concern for the electric network outside the plant. It's going to protect itself.
Yeah.
I think the answer to the question that was raised is, in a
Yes.
circumstance like that, uh, the whole thing is going to shut down.
Yeah. Professor, one more question is there, and Sansad is again asking one more question. Is the oscillation in frequency response that followed immediately after the frequency another is caused by the reactive power the grid was handling?
I can't. I think I understand the question. Oscillation for
Yeah, oscillation in frequency response that followed immediately after the frequency another is caused by the reactive power of the grid was handling. That is, it is handling or not? That's the question. I think so.
the if you look at it, here's how I answer that question. This is not a direct answer to the question, it's indirect, but I think as an indirect answer, it might help. If I take a power system, whether it be rotating synchronous generators or electronic inverters, makes no difference to this. I can and I take a system that's spread out over a long distance, where a long distance would be 500 miles from somewhere in Florida to somewhere in New York, or what is it, 800 miles from somewhere in Gujarat to somewhere in Maharashtra state, or somewhere in 500 miles in Brazil would be Sao Paulo to Rio de Janeiro. If you're talking about a power system that's spread out over distance, where that means it's spread out over series reactance and transmission lines, you see this characteristic of a system. When there's a frequency disturbance at one place in the system, the frequency disturbance is felt everywhere in the system. If you have a generator Well, I have an example that's, I don't have the slide handy, but I'll describe it by words. If I have a sudden loss of generation in Florida, it's in the
Mhm.
southeast of the USA, the frequency in Minneapolis, which is in the northwest of the USA, will follow the frequency in the southwest very closely. Frequency disturbances, real power disturbances, propagate across the AC transmission network rapidly and everywhere. On the other hand, if I have a bad reactive situation, let's say in the middle of the continent in Kansas City, or in the middle of India, would be where would that be?
Mhm.
Bhopal. Uh, the reactive power disturbances don't travel very far. They tend to be very severe in the local vicinity of the event. But if you have a bad reactive event, a sudden loss of a generator or a synchronous condenser, and a loss of a lot of reactive power, a lot of the capacitor bank shorting out in the center of the system, the voltage disturbance around the edges of the system will not be nearly so severe.
Yes,
Voltage
yes,
voltage events don't propagate, and real power events do propagate. There's a phase difference, a phase delay between an event occurring in California and an event occurring in New York. It takes frequency doesn't change instantaneously in New York when it changes in California. It follows, but it follows with a time constant of a few seconds. So there's a phase difference between what's going on in California and what's going on in New York. Well, to be exact about it, let's say there's a phase difference between what's going on in British Columbia in Canada and Arizona in the USA. The distance is about 1,500 miles. The reactive uh, uh, displacement between the reactive, uh, sorry, the distance is
yeah,
1,500 miles.
yeah.
The phase angle spread
This
between
angle is, yeah.
the
So the
sending
arms
and
network, yeah.
receiving end is perhaps more than 100 degrees, but there are many generators along the way, so the system's stable asymptotically.
Yes, yes,
If you
yes.
have
Right, right.
a real power event, you are liable you're going to start an oscillation, but the oscillation is going to be because of the time phase, uh, time delay that it takes from an event to
Yes,
affect
yes.
frequency in Arizona. That affects frequency in Nevada. That affects frequency at the south side of Oregon. That affects
Mhm.
frequency on the north side of Oregon. That affects
Mhm.
frequency in the center of Washington. And finally, that affects frequency in Alberta or British Columbia. The connection is strong. The frequency, as remember this, you've got the main frequency and then the sizzle.
Yeah.
When you see oscillations in real power, that's the
Yes,
sizzle in frequency. It's associated with reactive power difficulties because the voltage. If you take a large power system, look, I'm going to do this. I'm going to try an experiment here using my hands on television on my Macintosh computer with an audience in Europe and India and China. But can you see my hands?
yeah.
My left hand is the voltage phaser at one end of the power system. My
Okay.
right hand is the voltage phaser at the other end of the power system. The center of the power system is the tips of my fingers. The generation at one end of the power system is my left wrist. The generation at the other end of the power system is my right.
Right. Yeah.
I'm operating with a small power transfer and strong voltage in the middle of the system. Something happens. Power needs to flow from my left hand to my right hand.
Right hand.
That
Yeah.
requires the phase angle to spread out. And the stability of that's determined by the famous equal area criterion of
Okay.
power system textbooks from the
Yeah.
1930s. But by geometry, if the length of my hand is 1 per unit voltage, and the length of my hand is
Yes.
1 per unit voltage at the sending and
Voltage.
receiving,
But the phase angle will be different.
but I
Yeah.
swing them
Right.
out a long way apart, then the cord across the middle says the voltage in the middle goes down.
Yes.
So there is necessarily, by the most basic concept of power transfer in an AC system, the oscillations and unstable oscillations of power flow, which are because of oscillations of phase angle,
Yes.
are associated with the by geometry with the voltage in the middle, which is the radial to the chord between the two voltage sources. So
Yes. Yes.
a,
Yes.
a
Right. Right. Bro.
partial answer, a partial answer to the question is that. A more complete answer would be uh, that's what the connection between the power oscillations and voltage oscillations is what led to the invention of the power system stabilizer and
Yeah.
the entire analytical theory of
Yeah.
how the voltage
It's
oscillation
about the power system stabilizer and the
relate.
proper damping control of oscillations and all.
Yeah.
Yeah.
I don't think we know enough about how that's going to happen with electronic inverters because we
Yeah.
don't know. We know the control scheme of a generator, its transfer function, and the voltage regulator and its transfer function. We
Yes.
know
Yes.
the operation of an inverter when everything's changing slowly enough that phase lock loops behave nicely and phase
Yeah.
angle measurement behaves
Yes.
nicely. But I don't know that we have enough experience to know what's going to. I don't think our analytical tools are good enough yet to be authoritative about how it's going to happen when everything's electronic.
Yeah, yeah, yeah. By the implementation of latest VARMS technology in facial measurement unit and all advanced structures in signal processing, I think it will be in betterment stage right now. Maybe. Yeah.
There's going to be plenty of fun
Yeah.
to be had in the development of the
Yeah. Right. Right.
basically point on wave software that we're going to need. We need it now. So those of you that are in graduate research programs and PhD
Yeah, 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 yeah. Basically I know so many American universities itself. I think maybe in a Washington State University, Mani Venkata Subramaniam, and I met so many people in the same area working on the stability area and these things and oscillation studies and all.
yeah,
Yeah,
I'm hoping that we'll see a lot of progress coming now from the universities of the world in the analytical tools that we have. In the same way that we saw such great progress in the mid 1960s as the computers started to expand in the universities
yes,
like
yes,
Northwest, Professor Van Ness and people that were looking at the early days of the large matrix operations were
yeah,
contributed from universities and Bonneville Power 50 years ago.
yeah. So I think we are going above the time and all. So actually, it was a very comprehensive presentation. I liked very much the basic fundamentals. So, so many, not many bigger things and all. So it's completely precise one. I like it very much and. Very good interactive session with you, sir. So nice to be with you at the time. Meantime, I invite Straji for the vote of thanks for this particular event, and thank you. Once again, thank you for John. Thank you.
Well, thank you all, wherever you are. Thank you for listening.
Thank you,
Hi, Straji. You
Rahul.
can, yeah, yeah,
Thank you, Rahul, and thank you, Dr. John, for joining us today. So, a warm and graceful day to our most valuable, honorable chief guest, Dr. John Undrill, and the moderator, Rahul Satish, our organization team, and all the participants watching us online. It's my privilege to propose a vote of thanks. So, on behalf of IEEE I extend a vote of thanks to Dr. John Undrill, who spared time from his busiest schedule. Thank you so much, sir, for taking this keynote session. I would like to express my gratitude to John for gracing the occasion and sharing his valuable knowledge today. I am immensely thankful to Rahul Satish, our moderator, for his efforts. I need to mention my deepest sense of appreciation to Rahul. I also extend thanks to all PSYP team members and PFS task force team for their enormous cooperation and support. Last but not the least, a big thank you to all our participants who made this session very memorable to all of us. And I would like to request our participants to kindly fill the feedback form given in the comments so that we can strive to improve ourselves. We have two more sessions tomorrow. One is an entrepreneurship track from 2:15 to 3:15 p.m. UTC, and a keynote session on the topic resilience value and matrices of grit from 3:15 to 4 p.m. UTC. So thank you all, and see you tomorrow. I would like to
Thank you.
ask our chief guest John Undrill and Rahul to stay back for 2 more minutes so that we can take a virtual photograph to create a memory for ourselves.